Greetings to Prof. Ho. Today we're going to present our group assignment entitled Unveiling the Dynamics of Real Analysis. Our members consist of 5 people, which is myself, Emanuela, Akila, Nadira, Samiatu, and Shaswana. So, there are 4 content for our assignment, which is the history, the application, the games, and the conclusion. The development of numbers and real analysis has a long and complex history that dates back thousands of years. It all started with the development of numeral system based on counting and symbols by early civilization, including the Egyptian, Babylonians, and Chinese. The decimal system and the introduction of zero by Indian mathematicians were major contributions that eventually led to the development of the universally accepted Arabic numeral system. On the other hand, the focus on geometry and number theory at this time was on the ancient Greeks, who laid the groundwork for later mathematical advancement. The rediscovery of ancient mathematical knowledge during the Renaissance led to improvements in logarithms and the unification of algebra and geometry. Real analysis has a long history that has been shaped by the efforts of many mathematicians, as well as the continual development of rigorous mathematical methods. Real analysis has its roots in classical Greece, where philosophers like Zeno of Elea and Eudoxus of Cnidus laid the foundation. Zeno's paradox raised philosophical questions about the nature of infinity and the concept of limits, whereas Eudoxus developed a method of exhaustions, a precursor to the modern concept of limit, to study geometric shapes and their areas. The invention of calculus in the 17th century marked a key turning point in the development of real analysis. Isaac Newton and Gottfried Wilhelm Leibniz independently developed differential and integral calculus. Newton focused on his method of fluxions and the calculus of finite differences, while Leibniz introduced his notation and integral calculus. Their work provided powerful tools for calculating rates of change, areas, and solving various problems in physics, engineering, and mathematics. However, it was not until the 18th and 19th centuries that the true analysis took shape as a formal discipline. Mathematicians like Augustin Louis Cauchy and Carl Weierstrass laid the foundation for calculus. Cauchy defined boundaries, continuity, and the standard definitions of a derivative. Weierstrass focused on the concept of uniform, continuity, sequences, and series. George Cantor studied the concept of sets and introduced the concept of cardinality and various sides of infinity. Cantor's work on set theory was crucial in understanding the structure of real numbers and infinite sets. In the 20th century, real analysis continued to evolve in the emergence of functional analysis and complex analysis. Functional analysis is the study of vector spaces and operators and was pioneered by mathematicians such as David Hilbert and Friedrich Ries. Complex analysis is the study of complex number functions and was pioneered by mathematicians such as Bernard Riemann and Pierre Fatou. Measure theory is the study of how to measure sets and was pioneered by mathematicians such as Henri Lebesgue. Measure theory and Lebesgue integration theory have given rise to new techniques for analyzing function and measuring sets, which was allowed for a deeper understanding of the properties of real numbers.
Steady-state heat equation. This section aims to develop the partial differential equation that describe heat flow on surface using physical principle. We are considering the problem of determining the temperature on a thin metal disc. We assume certain assumptions to evaluate this problem. First, we assume that the system is at equilibrium, which means that it is in steady state. This assumption enable us to focus on the spatial distribution of temperature without considering any temporal changes. So working in polar coordinates help us utilize the disk symmetry. This is also known as the steady-state heat problem. According to the law that governs heat flow across boundary state, the amount of heat that moves over the heat flow is proportional to the temperature difference between the two sides of the boundary. We must take into consideration the infinitesimal version of the temperature change since we are dealing with a continuous temperature distribution. We may derive a partial differential equation that describes the steady-state heat flow on the disk by considering the normal derivative at every point on the boundary circle. In terms of mathematical formulation, the steady-state heat equation can be expressed as Laplace equation or the heat equation, depending on the context. For Laplace equation, it describes the equilibrium behavior of the temperature distribution without considering any time-dependent changes. By solving Laplace equation, we can determine the temperature distribution on the disk under steady-state condition. And if we were interested in studying the transient behavior of the temperature distribution over time, we would use the heat equation. However, in the case of the steady state, where the temperature remains constant over time, the time-dependent term in the heat equation becomes zero, and it reduced to Laplace equation.
Now, I will talk about the second application, which is the application of limit and continuity in the market equilibrium analysis. Let's get to know what is the market equilibrium. It is an interaction between consumer and producer in a free market based on what Maslow 2014 said. And now, what is the perfect equilibrium? The perfect equilibrium is when the quantity that consumers are willing to buy are equal to the supply that producers are willing to produce at a certain price. Why the market equilibrium is important? Because it gives us the insight of the market stability, price formation, and the resource allocation based on what Samuelson and Nordau said in 2019. Right now, let's understand the concept of limit and continuity because it is essential for us to evaluate the market equilibrium theory. Limit in mathematics, it refers to the idea of closeness. Meanwhile, in analysis, you can see the definition as stated in the slide. This concept is vital for academics as it helps them to evaluate the function behavior, continuity, and properties. Now, continuity. Continuity defined as a continuous function that reads consistently across its domain without abrupt changes. Exhibit continuous and connected behavior, which means that minor change in input will result in minor changes in output. In market equilibrium analysis, the continuity of demand and supply function is vital as it helps determine the existence and stability of equilibrium points.
So here is the application. The upper square shows the notation that have been used, and the below square is the analysis of market equilibrium using the concept of limit and continuity.
Lastly, in real-world application, by analyzing the behavior of demand and supply function using demands, economists can assess the convergence or divergence of this function as price approach equilibrium levels. This evaluation allows them to determine the existence and stability of equilibrium, providing valuable insight into the balance or imbalance in the market.
The third application of real analysis is Newton's method. Newton's method is an iterative method for rapidly computing the zeros of differentiable functions. The contraction principle gives a nice proof that this method works. Suppose we have a function f on set of real numbers r and a reasonable guess x0 for the zero or root of f. If f is differentiable at x0, then we can draw the tangent line at x0. It seems plausible that if x0 is close to the root of the function, the root of the tangent line will be even closer. This uses one of the basic ideas of differential calculus. The tangent line to f at x0 is a good approximation to f near x0. Computation of square roots. Newton's method is an excellent way for a person or computer to find square roots rapidly to high accuracy. To illustrate the value of the method and of quadratic convergence, we'll compute a square root. It also gives an upper bound for the error between the computed value and the true value. Finding the square root of a more than 0 means finding the positive root of the function fx equal to x squared minus a. Applying Newton's method, a simple computation gives Tx equal to 1 over 2 times x plus a over x. Suppose that we are computing square root 149 to 20 digits of accuracy. Since 12 squared equals to 144, which is less than 149, and less than 169 equals to 13 squared, let x0 equals to 12 be our first approximation. Clearly, the error is at most 0.5. Moreover, t prime x equals to 1 over 2 times 1 minus 149 over x squared. This is evidently monotone. Thus, on 1213, the derivative is bounded by 10 over 169 less than 0.06. Therefore, the Newton's method guarantees that the sequence x0 equals to 12 xn plus 1 equals to 1 over 2 times xn plus 149 over xn for n more than or equal to 0 converges quadratically to square root 149. Let us compute the other constant involved as f prime x equals to 2x and f double prime x equals to 2. We obtain a equals to 2, b equals to 24, and m is equals to 0.084. From the error estimate for Newton's method 0.21, we obtain modulus x n plus 1 minus x less than or equals to 0.084 modulus x n minus x squared. Starting with x0 equals to 12, we have the following table of terms and bounds on the error. When n equals to 0, xn is 12 and it bounds on 0.21. We already have 20 digits of accuracy at n equals to 4.
The real number system can be understood through engaging games like the one played by Anita and Jake. In this game, they select numbers within the unit interval 0, 1, following specific rules. Anita starts by choosing a number, then Jake picks one between Anita's choice and 1. This process continues, forming a sequence. The limit of this sequence, denoted as alpha, represents as a real number between 0 and 1. Anita wins if alpha is in a fixed subset S, while Jack wins if alpha is not in S. These games help us grasp the fundamental concept in real numbers and their properties. Countability is a fundamental concept in mathematics. A set is countable if its element can be listed in an infinite sequence. Potentially with repetitions, it can also be determined by the existence of a surjective function from the natural numbers onto the set. Uncountable sets, on the other hand, cannot be listed in such a manner. The renowned mathematician Cantor proved that the real interval 0, 1 is an uncountable set using his diagonalization argument. However, we can present an alternative proof based on the game played by Anita and Jake. If a set S is countable, then Jake possesses a winning strategy. This strategy involves choosing elements from S whenever possible and any permissible number otherwise. By consistently implementing this approach, Jake secures victory, indicating that S cannot be countable. Through engaging games and innovative approaches, we unravel the mysteries of mathematics and gain deeper insights into the real number system. In a game where Jake makes moves based on certain conditions, he consistently wins. When the set S is 0, 1, Anita always wins. This shows that the interval 0, 1 is an uncountable set. We can prove this by analyzing perfect sets, which are non-empty sets equal to their set of limit points. Every perfect set is uncountable. Using an infinite game, we can provide an alternative proof. The infimum of a subset X of 0, 1 is denoted as Y equal to infimum X. We can also define approachability from the right and left in terms of open intervals. In the study of perfect sets, we find that a non-empty set X is perfect if and only if can be approached from the right and left. Lemmas 1 and 2 provide insights into approachability within perfect sets. Using these lemmas, we can prove that if a set is perfect, Anita possesses a winning strategy. Consequently, every perfect set is uncountable. This leads us to corollary 2.
In conclusion, throughout this rich history, mathematicians from the ancient Greeks to the modern era have made significant contributions to the development of real analysis. The application of real analysis are extensive, with its principles and techniques being employed in various scientific disciplines, engineering, economics, and computer science. Furthermore, the teaching and understanding of the real number system can be facilitated through interactive games that introduce basic concepts. Real analysis continues to play a pivotal role in understanding complex phenomena and solving real-world problems, making it an indispensable and fundamental discipline in modern mathematics and scientific research. That is all from us. Thank you.